Okay, welcome back. So actually, before we go into the details of connecting heat capacity and specific heat to this particle model of thermal energy, there are a couple of things that I briefly wanted to cover. One is polyatomic molecules, and then thinking about how do we connect this idea of your system having some average kinetic energy to average speed of atoms in your system. Okay, so this is just a review of everything we've seen so far. We argued that solids must have 6 total number of modes and liquids as well. Monatomic gases only have 3. And then diatomic gases have new ways that they can store energy, either through rotations or vibrations, because now we have a bond between these diatomic molecules. We will look at it, I think, in the next recording a little bit more deeply into this idea of freezing modes. But the main idea is there are total number of maximum 7 modes that a diatomic molecule can have. But sometimes it's 5 when the vibrational modes are frozen. Okay, so far we've only looked at these 2 specific types of gases, but you can imagine a gas consisting of some more complex looking molecules. So, something like this, which has many atoms, this molecule, and it's also not linear. So what makes linear versus nonlinear important is the availability of these different rotational modes. So when your molecule is linear, there's that one symmetric axis that does not allow for energy being stored in that rotation. However, when your molecule is not linear like this, or it's not symmetric about any specific axis, then now we're going to have 3 rotational kinetic energy modes. Okay, so when it's something more complicated like this, how do we go about figuring out what is the total number of possible modes? Well, a simpler way of thinking about this, and I'll kind of describe this quickly now, but there's going to be an entire DL activity where you're going to really go step by step thinking about this process of counting modes for complex molecules. Okay, so one way of thinking about it is you can think about it. So imagine this molecule has n atoms. So in this case, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 here. It could be any number. So one way you can think about it is, let's first determine what's the possible number of total kinetic energy modes. And the way you can visualize this is, imagine that each atom is an individual atom, which has those translational kinetic energy modes. And there are 3 of them in 3D. So the total number of possible kinetic energy modes is 3 times n for n atoms. Now we can categorize these in terms of the 3 types of kinetic energies we've discussed. So there's a translational kinetic energy, that's just this molecule is a whole moving in 3-dimensional space. Then there's a rotational one, and in this case there are 3. As I discussed, it's not linear, so you can either rotate this way on the surface of this slide here. It can rotate in and out of the board this way, or about its axis this way, so kind of in and out of the board that way. So that's the 3 independent axes. And then, so that only equals to 6, but we know the total has to be 3n. So all the modes that are left are due to these vibrations. So it's not as simple. So we knew that when I was a diatomic molecule, there was that one vibration relative to each other, but it's not so simple unless you really know the details of chemistry and which modes are, or which types of vibrations are independent. We cannot just look at this and decide how many vibrational modes there are. So we're going to use this method to count them, knowing that the total number of kinetic energies has to be 3n. So it has to be 3 plus 3 plus 3n minus 6 to give us 3n. So this number, what's left behind, is exactly for those vibrational modes. But we have to remember that for every vibrational mode, it has to, for every kinetic vibrational mode, it has to come in pairs with potential energy modes, because you can't have vibrations without both kinetic and potential modes. So that means we have to have the same number of also potential modes, which is 3n minus 6. So then finally, the total number of possible modes, assuming none of them are frozen, is going to be our kinetic number, which is 3n, plus a potential 3n minus 6, so a total of 6n minus 6, as it's written here. So that's kind of the basic idea of trying to figure out. Now, a task I will leave for you to do on your own, and I believe it could be an FNT as well, is to do this same kind of logic, but for a linear complex molecule. How is it going to be different for a linear one? We're going to go, instead of having 3 rotational modes, now we'll have only 2 rotational modes. So think about how that will change your sum of the total number of modes. Okay, and now I'll just ask you a couple of questions. So another concept that we actually want to think about, and we'll do it through this question, is connecting a kinetic energy to speed. So let's read this together. So on average, the speed of atoms in 5 moles of a monatomic gas compared to 2 moles of a solid made of the same substance, if they have the same total thermal energy is. So we have these 2 substances, 5 moles of a monatomic gas, 2 moles of a solid. They have the same total thermal energy. Now let's think about, does that mean that the speed on average of each atom within this gas or solid, are the speeds the same? Is it faster? So we're comparing the gas to the solid. So is it faster in the gas, slower in the gas, same, or there's not enough information? So how do we connect speed to everything we've been doing so far? Well, we have to recall this equation from the beginning of the quarter. K equals to 1/2 mv squared. So you will first think about how is the average kinetic energy compare, and then from that you'll be able to conclude something about speed. And then here's another equation you need to think about this. All right, so take a minute, pause the video, think about it, come up with your best answer, and let's take a look. Oh, okay. So it turns out that in the gas, on average, the atoms are gonna be moving slower. So let's think about why. Okay, so we know that we have the same total thermal energy. So that's kind of the logic here. Okay, so we know the same total thermal energy, then we can use this equation to compare the temperatures. Once we can compare the temperature, we can express kinetic energy in terms of temperature, knowing that there's 3 modes, and then from that we can compare it to speed. So there's quite a few steps here in our thought process. Okay, so first let's set the thermal energies equal to each other and make sure we count correctly the total number of modes. So 5 moles monatomic gas, here's a 5 Na. Monatomic gas means 3 modes per particle. Then this 1/2 kBt of gas. Now we're comparing this, so same amount of energy is 2 moles of a solid. So the 6 is for the modes per particle in a solid times 1/2 kBt solid. Now which temperature will be greater? Well, let's look at the prefactor. Here's 15 and here's 12. So bigger number has to be multiplied by a smaller number in order to have the same number on this side. So the T of gas, and you can even find the ratio, it's going to be 12/15. So the T of gas has to be smaller than the temperature in the solid. So the gas is at a lower temperature. What is that? So intuitively you would think, okay, lower temperature means they should be moving slower, and that's the case. So what is the average kinetic energy in the solid versus gas. Also keep in mind, we're talking about different types of kind of motion, because in the gas, it's the translational energy of the particles moving around everywhere randomly. And we're comparing it to this vibrational average kinetic energy as the particles are vibrating in the solid. But it's completely, they have the same units. It's, distance per unit time. So it's okay to compare them, although they're different sources of kinetic energy. Okay, so the kinetic energy per particle, so that's kind of the average kinetic energy that each atom will have, is going to be 3. Both the gas and the solid have 3 kinetic energy modes. Right? The solid also has the potential ones, but that's not relevant here. We're only focusing on kinetic energy. So there are 3 there, times this factor of 1/2 kBt, has to now then equal to 1/2 mv squared if we want to compare it to speed. So the higher the temperature, we could see this relationship between V and T. The higher the temperature, the greater the speed in this case. So we were comparing the gas to the solid. Gas has lower temperature, so that means slower speed. So it's going to be moving slower. Now with these problems, there's one subtlety you have to be careful about, and maybe that's the next question. No, no, it's not related. Okay, so let me just mention it now. There's also, when we're comparing kinetic energy to speed, there's also a factor of mass here. So you have to be careful about that. You can't just conclude if something has a smaller temperature, automatically the particles are moving slower. That's only true if we're talking about, so here was true, because we're talking about same substance. So this word same substance is key there. That means that the atoms have the same mass. But imagine that instead we were comparing a gas with very heavy atoms compared to a solid with lighter ones. So even though it had gas has a smaller temperature, maybe because it's heavy enough, the the net effect, or actually, let's say they were light. No, I got it reversed. So let's say the gas particles were light and the solid ones are heavy. So although the temperature is smaller, you would think, okay, speed has to be slower. But if the ratio of the masses is significant enough, then that effect might be dominating, resulting in actually the gas particles moving faster. So you have to, in those cases, take the mass into account too. Here we didn't need to, because again, we're talking about the same substance, so same mass. All right, let's take a look at a slightly different scenario now. So here, what you want to do is you want to increase the temperature of 2 substances by the same amount. So the temperature, you're changing that by the same amount. But you discover, and you have 2 separate substances present here. You discover that it takes double the amount of energy to increase the temperature of 2 moles of some unknown substance. So you don't know what that substance is, compared to 1 mole of a monatomic gas. So you put in double amount of energy to this unknown substance compared to 1 mole of a monatomic gas to get the same change in temperature. So the question is, can you conclude anything about this unknown substance? Is it a solid or liquid, a monatomic gas, diatomic gas with vibrational modes frozen, or diatomic gas with active modes? So basically, this question is asking you, can you figure out the modes per particle based on this information for the unknown substance? So pause the video, think about it, use this equation to help you. And let's take a look at the answer. So the answer is a monatomic gas as well. So why is that? So let's start by figuring out the total change in thermal energy for a monatomic gas that we know, the known substance. So there's 1 mole of it. This 3 is the 3 modes per particle for monatomic gas, and this factor of 1/2 kb delta T gives us 3/2 Na Kb delta T. So that's how much energy we put into a monatomic gas. Now for the unknown substance, we know that we added double this energy. So 6/2 NaKBT. And let's now separate the delta E thermal for the unknown substance in terms of the total number of particles and modes per particle. So what is unknown about this substance is how many modes per particle. We know that we have 2 moles of it. So 2 Na times this unknown modes per particle times 1/2 kBt. And the delta T is the same for the gas, for the monatomic gas and the unknown substance, because that's what you were given. That you added the double amount of energy, but you got the same change in temperature. So then if you compare these numbers, we need something that's 6/2. Now we have here over 2. So 2 times 3 will give you 6/2. So what is the only possible substance that has 3 modes per particle? That's a monatomic gas. And this kind of makes sense. We have the same substance now, monatomic gas. If you have double the number of particles, you will have to add double amount of energy to get the same temperature change. All right, in the next recording, we will start now connecting specific heat to this idea of modes. So that's coming up next. Thank you for listening.